All right, in this last video of section 3.9, I'll be going over example 7. So example 7 says, a metal frame in the shape of a box has a square base. All right, so I'm going to kind of write that down. So if the base is square, I know that these two dimensions, I'll call them x, has to be square, right? The base is square. Okay, the vertical bars are a different material than the horizontal bars, okay? If the horizontal bars expand at 0.001 centimeters per hour, all right, so horizontal bars is what I call the x. I'm gonna just start writing this information down as we go because it seems like we have a fair bit. So the horizontal bars expand at 0.001 centimeters per hour, right? That's one piece of information. So I know dx dt, the rate of change in those bars, is 0.001 meters per hour. Okay, next it says, and the vertical bars expand at, so the vertical bars expand at 0.002 centimeters per hour. All right, so since these are different, I need to give these vertical bars a different name. I'll call them y. So I also know, this should say no, I also know that rate. Therefore, we have dy dt is equal to 0.002 centimeters per hour, and this should be centimeters too. There we go. Okay, let's read on. So next, the question is, how is the volume changing at the moment the area of the base is 9 centimeters squared and the volume is 180 centimeters cubed? Okay, so we want how the volume is changing. Okay, so that would be dv at the moment when, so that would be a time, so dt, so we want dv dt when the area is 9 centimeters squared and the volume is 180 centimeters cubed. Okay, so it looks like we pulled all of the information out of here. Now what we're going to have to do is set up an equation and start tackling the problem. All right, so what I'm thinking is we have this metal frame, guessing it's warm or something because it looks like the bars on both are expanding, and you know, when things heat up they do expand a little bit, so that's probably what's going on, and that would naturally make the area of the base and the volume expand as well. We just want to figure out, okay, well, how quickly is this happening to the volume? So first we want to consider all of the equations that we have. Okay, so we know we have x, we have the volume, and we have y. So we need an equation. So we need an equation to relate x, y, and v. Right? Well, an equation that we can use for that would of course be volume of a cube. You could call it a box, but either way we'd have v equals x squared times y, because the volume of the shape is given by length times width times height. So x times x is x squared, and then our height is y, so x squared times y. Right, now that we have that equation, we need to go ahead and take our derivative. So taking our derivative, we'll do that with respect to t, since our rates are all with respect to t in this example. So the derivative of the left of volume is dv dt, okay, equals, we have a product, x squared times y, so we need to use the product rule on the derivative of the right. The derivative of x squared with respect to t is going to require the chain rule. So the derivative of the outside is 2x. The derivative of the inside would be dx dt. So that would be the derivative of the first times the second is times y, plus the first is x squared, times the derivative of the second would be dy dt. So the derivative of y with respect to t. All right, now we need to go ahead and fill in what we have. So fill in or substitute in our given information. All right, we don't know what dv dt is. That's what we're trying to find. So I'm just going to rewrite that. Okay, I'll rewrite the 2. We're not directly given an x, so I'm just going to have to fill that in for now. We do know that dx dt is 100 centimeters, sorry, 0.001 centimeters per hour. Okay, we do not know y yet, so I just have to rewrite that. Okay, I'll rewrite the x squared because again we don't know x squared. We do know that dy dt is given as 0.002 centimeters per hour. Okay, so we can see in this right now we have only one equation with 3 unknowns. So we don't know dv dt, we don't know x, and we don't know y, right? This means that we need to take some of our other given information to find these pieces that we're missing. So in order to actually find a value for dv dt, we still need x and y. Okay, well, we have more given information to use, right? We know what our area is. Okay, we know what our area is right here. And we know what volume we're working with. So what we can do is use the area and the volume to find these values and then plug them in. All right, so doing that, let's see, I guess I'll use green. So I know the area of the base is 9 centimeters squared. Right, well, I also know, based on my symbols, that the area of the base is x squared. So I have x squared, which is 9 centimeters squared. Right, so here, if you take the square root of both sides, we get x equals 3 centimeters, right? And then on that, it wouldn't make sense to keep the negative solution. So one question I always get when I teach this is, why don't you do plus or minus? Well, if you think about that, if I used x as -3, that would be like saying my box has a negative side length, which doesn't make sense logically. So we would just keep our positive solution. All right, so now we need to find our y value. So since, I have to box this little guy off, there we go. Okay, so since we know the volume is x squared times y, and we're looking at volume being equal to 180 centimeters cubed, what I have is x squared times y equals 180 centimeters cubed, right? I know my x value is 3, I just calculated that, so really I have 9y equals 180 centimeters cubed. Technically, this is centimeters squared because my x squared was centimeters squared. I guess I'll write that out just to show you. Okay, so we have 9 centimeters squared times y is 180 centimeters cubed. So we get y equals 180 divided by 9 is 20. And that'd be centimeters because we'd have centimeters cubed divided by centimeters squared, which is left in centimeters, and that makes perfect sense because y is a side length, so our units look good. All right, so I'm out of space on here, but I have confidence that you can finish this. So what you're gonna do is just go ahead and plug these values into the original, and that will get you to the answer. So from here, you're just gonna plug in, all right, into this equation over here. Okay, if you want to, you can unit check, so you can put all the units in there, and you should find that at the end you get a centimeters cubed over time was in hours. There we go. Okay, so seen several examples. The beginning of your homework will